Okay, so welcome. It's a pleasure to be here. So I'll be talking about entanglement, gravity, and tensor networks. So the motivation for this discussion is to understand better how quantum gravity works and how the degrees of freedom of quantum gravity are encoded, how holography works, how do we describe the black hole interior, and the basic tool we are going to use is to study the patterns of entanglement, so understand better the structure of the wave function and how the degrees of freedom are entangled. So in other words, we are trying to follow the qubit, so understanding where qubits go. So the outline of this talk will be the following. So we'll start with some ancient concepts, so discussion of the quantum entropy and some of its properties. Then we'll discuss the quantum entropy in quantum field theories in the context of relativistic quantum field theory. Then we'll discuss it in the context of semi-classical gravity. And then we'll discuss quantum entropy in holography. And then we'll discuss some aspects of wormholes. And finally, we'll discuss some tensor networks. Okay, so quantum entropy. So the state of we imagine a quantum system characterized by a state given by a density matrix rho. Then we define the quantum entropy is defined by this formula, so the von Neumann entropy. Now, there are some associated useful concepts, and one useful concept is the modular Hamiltonian, which is just simply the log of the density matrix. And the reason for introducing this quantity is that in terms of this quantity, the density matrix looks thermal. So it looks like a thermal density matrix with temperature 1. And this has some useful, well, it's useful for reasons you'll see in a moment. It's mainly useful when you are comparing two density matrices. So there is a concept called relative entropy. Given two density matrices, you can define the relative entropy by this formula here. If you think of sigma, in terms of the modular Hamiltonian of sigma, you think of that as a ordinary Hamiltonian, then this relative entropy is just simply the free energy, or the difference in free energy between the state rho and the state sigma, where here the energy is given by the modular Hamiltonian. Of course, this can be defined regardless of whether sigma is given by the actual dynamical Hamiltonian or not. So in the cases where sigma is just given by the thermal density matrix for the actual Hamiltonian of the system, then this definition is just simply the free energy, or the difference in free energy between the state rho and the thermal state. And this density matrix, this relative entropy, is a measure of the distinguishability of states of sigma and rho. And so it has a bunch of properties that support this interpretation. One is the fact that it is positive, and it's actually equal to 0 only when they are equal, when sigma and rho are equal. And then the other non-trivial property is that it's monotonic. So if you have if B is a subsystem of the system A, then you can restrict both density matrices to the subsystem B, and we can call those rho B and sigma B. And then the relative entropy of those two density matrices is less than the one for the original density matrices describing the system A. So this inequality is saying that if we restrict the operator algebra, so we look at less operators, then we can distinguish these two density matrices less. So the bigger the relative entropy, the more distinguishable the two density matrices are. And this inequality underlines a lot of the proofs that one can find in quantum field theory. So when we go to quantum field theory, then we can consider quantum entropy in quantum field theory. And a useful configuration to consider is to restrict attention to a subregion of the full space. And then even if we had a pure state in the full space, when we restrict to a subregion, we will have a mixed state, and we can calculate the entropy of that mixed state density matrix. And that entropy is divergent, but the divergences are well understood. The leading divergence in 4 dimensions is proportional to the area divided by the cutoff square, so it's a quadratic divergence, and it comes from the short-range entanglement between the degrees of freedom near the boundary of the region. And then there are some other subleading divergences, and then there are finite contributions. And most of the recent activity has centered in understanding the properties of the finite parts. Now, one motivation to study this is we should recall that quantum field theory is a target for what we should approximately get in the bulk, for example, in holography, or is certainly a target for the theory of quantum gravity, should reduce at low energies to quantum field theory. So certainly understanding entropy and the entanglement properties of quantum field theory is a crucial point. Now, an old result that is very basic in this is we can consider half of space. So we start with a theory in Minkowski space, and we restrict the attention to half of space, and then that implies we're going to make observations purely on here the right Rindler wedge. And in this case, the Lorentz symmetry of the quantum field theory and also some analytic continuation from Euclidean space implies that the density matrix on the right-hand side is thermal, and it's just given by a simple expression in terms of the boost operator, or which is the same as the Rindler Hamiltonian. So an important property of this density matrix is that it's the exponential of a simple operator, an operator which is just the boost generator, is a local integral of the stress tensor. So this happens for this very special region, which is just half of space, and it's a very basic property of quantum field theory, and it is of course the statement of the Unruh effect, and it's also related to Hawking radiation for black holes. Now, this half-space configuration is useful for the following. So you can consider now relative entropy between two states. So one state is an arbitrary state that we can have on the full Minkowski space, and the other is the vacuum. So that the vacuum, I mean the density matrix restricted to that half space, and which had the thermal form that we saw in the last transparency. So as we saw, an important property of relative entropy in quantum field theory is that it is UV finite. So we saw that there were divergences in the definition of the entropy, but these divergences cancel when we compare the two density matrices. And so the positivity of this quantity implies that the entropy, the difference in entropy between the state rho in that subregion and the vacuum is less or equal than the expectation value of the boost Hamiltonian or the Rindler energy. And this can be interpreted as a statement of the Bekenstein bound, limiting the entropy that we can have in some region in terms of the energy times the size, and the energy times the size or times the distance to the origin is the Rindler energy. It is also possible to prove C and F theorems, particularly in 2+1 dimensions, where we cannot be proven in some other way. So certainly thinking about quantum entropy is a useful tool to derive results. Very recently, people derived a result on the integrated null energy condition. So this is, you take T minus minus and you integrate it along one null direction, but you do not integrate it along the other transverse dimensions, and you can prove that this is positive based on properties of the quantum entropy. So I'm just going to give a quick idea of the argument. So you start from these regions, the region A and its complement, and then you shift these two regions. You think of those as region B and the complement. And one important property is that region B is contained within A, and A complement is contained within B complement, and then we get corresponding inequalities of relative entropies. And if we start from a pure state over the whole Minkowski space, then the entropy part of this configuration, the entropy of rho, of the state rho, will cancel out if we do the sum of these two inequalities, and we'll get just something that involves only the expectation values of the modular Hamiltonians, and we'll get an equation of this kind. If we now use the expression for the modular Hamiltonian in terms of the boost generator, this just gives the difference of the two boost generators, and that difference is just simply the P plus. So this simply has proven that P plus is positive. Of course, we knew that already. So this is just the idea of the argument. The true argument actually uses two regions. One is a half wedge, and the other is a half wedge with some small displacements along the null direction, which are localized. And thanks to some previous results, you can prove this, this relationship. So that's what that paper I quoted does. Now, so those previous results were related to a study of the shape dependence of the entropy. So people have looked, and this received a lot of attention, so they looked at the simplest configuration is, let's say, a sphere in a conformal field theory that's related to this plane configuration by conformal transformation. And we can consider two small deformations of this sphere, and to lead in order the dependence on the entropy on these two deformations is fixed by conformal symmetry. And also, you can argue that there is an overall coefficient that is related to the coefficient of the two-point function of the stress tensor, sometimes called CT. And that fixes completely this dependence on the entropy. So the idea is simply that changing the shape is the same as sort of keeping the shape fixed and then changing the metric, and changing the metric is related to the insertions of the stress tensor. And this also allows to understand the universality of the corner entropy that had been observed previously. So if you have a region with a corner close to pi, then that has a general form given by CT also. Now another issue that's been studied a lot recently is the issue of defining entanglement for gauge fields. So in this case, if you think in terms of a lattice, you cannot quite separate the degrees of freedom because the links, because the degrees of freedom of the lattice live on the link. And in this case, you have a slightly different decomposition of the Hilbert space. So Hilbert space doesn't tensor factorize into two factors, but the Hilbert space can be expressed as a sum of tensor factors, and where the sum is over all possible values of the electric field in the adjoining region. And so this is the electric field on each of the links, so it actually depends on the whole function of the electric field on the boundary. And so these Qs can be called charges, and they simply correspond to the electric field. They are kind of like a surface charge that exists when you cut the space into two parts, and they contribute to, so when you calculate, when you have a density matrix, a density matrix is given by a density matrix in each of the factors, and also a classical probability distribution for each of these terms in the sum. And then the entropy is just given by the standard formula we saw before, plus a term related to the classical probability distribution. So that's for abelian gauge theories. For non-abelian gauge theories, there are some additional factors that I'm not going to discuss. And this is related to these horizon charges discussed in this paper. Not to the charges at infinity discussed in the same paper, but to the charges at the horizon discussed in that paper. And they were also previously considered by all these other authors. For gravity, we expect a similar story where the electric field is replaced by the geometry of the surface. And now the consequences of this for UV finite quantities just remain to be seen. So this is something that certainly is important for defining this object properly. But when we compute relative entropies, of course, we'll have to do this for both rho and sigma. And then in the end, we'll get some finite answer that contains all this information. But how this, what distinctive signatures this has for UV quantities remains to be seen. Now, so all of this was entropy in the context of quantum field theory. And now we can discuss quantum entropy in semi-classical gravity. So we consider the quantum field theory now in a gravitational background. And then there was a lot of work in understanding corrections to black hole entropy, both for BPS and non-BPS black holes. And I'm not going to review that, so I'm just saying that it exists. But one important point is that we can think of the entropy in terms of something that's sometimes called generalized entropy, or let's say the total entropy, as being the area plus the entanglement entropy of the fields outside the black hole. And this is a quantity that is UV finite in the sense that here the entanglement entropy is divergent. It's divergent. It has some 1 over epsilon divergence, but the Newton constant also at one loop has a one loop counter term which cancels this divergence. And so to understand this cancellation, for example, in the case of gauge fields, you need to use the results we mentioned before. So this particular combination has nicer properties, and is certainly what the corrected entropy is. Now one can prove the second law of thermodynamics using this formula and using the monotonicity of relative entropy. So of course, if we only looked at the area, that was done a long time ago by Hawking, but Aaron Wall understood how to prove it in the cases when you include the whole entropy, and that's important for situations such as an evaporating black hole where the area decreases while the entanglement entropy increases outside, and so he proved why the full entropy actually increases through this process, and it's just the consequence of that, basically that monotonicity of relative entropy that we discussed before. He didn't prove it in the most general case, but he proved it essentially for black holes and free fields. Now, other set of results involve understanding better the quantum Busso bound. Now, before I discuss the quantum Busso bound, I'll discuss the classical Busso bound, what we can call the classical Busso bound. We consider a bunch of null rays with a negative expansion. So the expansion is defined, so we have some null rays that span some transverse area. As we follow the null rays, this area can either increase or decrease. And we consider configurations where the area is decreasing, so where the expansion is negative. And if we consider null rays of this kind, then the Busso bound says that the entropy that crosses this null surface should be less than the difference between the initial area and the final area. So the final area is smaller because the area is decreasing, and so this is positive, and this bounds the entropy. Okay, now this requires, in the quantum mechanical case, it requires a better definition of the entropy because we cannot localize entropy in quantum theory. And so there are a couple of versions of what the quantum version should be. So there were two versions in the literature that were argued to be true, and I will discuss the second one. So the second one replaces this Busso bound by something they called the quantum focusing conjecture. And before I tell you what the quantum focusing conjecture is, I'm going to tell you about the classical focusing conjecture, the classical focusing theorem. Okay. So here you consider again the same concept, a bunch of null rays, and you consider the area that they span, and you can define the expansion. This could be positive or negative, but the focusing theorem tells us that as you go along the affine parameter, this should be negative if because the stress tensor, the null components of the stress tensor are positive. Okay, so that's the classical focusing theorem. So the quantum focusing conjecture consists of replacing the area that was appearing in the definition of the expansion by that formula of the generalized entropy. So area plus the entanglement entropy outside some region. And then we take the derivative with respect to the affine parameter. So we consider, let's say, some area and the entanglement entropy of all the fields along this region with the others. More precisely, we consider the area times the von Neumann entropy of the fields on this slice. That's at one time, and then we take the difference of that at some other affine parameter later. We take the difference, we define this so-called quantum expansion, and the conjecture is that this will always be less or equal than 0. This is a general conjecture, and it reduces to the classical Busso bound if you consider a configuration, a finite configuration of this kind, where the quantum expansion is initially negative, then the the generalized entropy here will be smaller than this one here, and that implies the classical Busso bound. And it also in the limit of weak gravity, so if you consider a situation where these null rays are almost not expanding, then if you throw in matter, they will expand a little bit given by Einstein's equations, and this quantum expansion conjecture reduces to the statement, to a field theory statement, that the expectation value of the stress tensor, the minus-minus component, should be bigger than this second derivative of the entanglement outside the region. And this was then proven in some cases, and in some cases means essentially free field theories or super renormalizable, so theories that are free in the ultraviolet. So to the extent that this has been proven, so the previous conjecture has been proven, so in some specific cases, and would be nice to understand it more generally. Okay, so that closes a bit the discussion of quantum entropy in the case of semi-classical gravity, and I should emphasize that these whole developments have been in the direction of understanding this entropy at one loop level, both area plus the correction, and proving various properties for it, the second law and this Busso bound. So now I'm going to discuss entanglement and holography. So if we consider entanglement in theories with gravity duals, we have this well-known formula that you've probably seen before that says that if you have some region in the boundary theory, so the boundary theory lives here on this blue line, and you have some region of space in this boundary theory, then the entanglement entropy of this region is given by the area of a surface, and the surface you should choose is one that has the minimal area. So you consider all possible surfaces, and you consider the one with a minimal area. So that's the result to leading order in the G-Newton expansion. Then various corrections were considered of this formula. So you can consider corrections that are curvature corrections. This can be considered in the context of black holes, and also in this context of entanglement entropy. This Ryuta-Kainagi formula is a generalization of the black hole entropy formula to configurations, to situations without a Killing symmetry. So these are all classical corrections. It would be interesting to know whether there is a string theory formula that resembles all these corrections, some string theory formula that would, some quantity that we can compute on the worldsheet. If we are given an exact CFT, we can compute this quantity on the worldsheet and we'll give everything here. This is a problem, an open problem both for this case and for the black hole case. We can also consider the one loop corrections, so the corrections that are of order 0 in G-Newton, and those are given by considering the entanglement entropy of the region enclosed by the Ryuta-Kainagi surface. And so we consider the von Neumann entropy of the bulk fields here, and that gives the one loop correction. Again, we get the same combination that we are getting for black holes of an area plus this entanglement entropy in the bulk. Now we've seen that relative entropy is a nice concept because it is finite, and so we can consider the relative entropy between two states in the boundary theory. And it turns out that this relative entropy is the same as the relative entropy in the bulk between the two bulk states. So this looks like a trivial formula saying that relative entropy is equal to relative entropy, but the left-hand side is some quantity that you think about in the boundary theory, and the right-hand side is some quantity you can define using the bulk field theory. And again, this formula is correct to order G-Newton. We don't know whether we don't know exactly what the form of the corrections will be here, of the G-Newton corrections. And this formula is based on the idea that the modular Hamiltonian of the boundary theory has a piece in the bulk that is given by the area, just the C number, so the area over G-Newton, plus the bulk modular Hamiltonian, so modular Hamiltonian of the bulk fields. Now here one can have 2 points of view on this formula. So one is the conservative point of view, which is to say that it holds only for semi-classical states. And the other one is a little more radical, more speculative, is to say that all degrees of freedom are visible in the bulk. So if And this is a cutoff independent indication that all of black hole entropy comes from the atmosphere. Again, this is a speculative remark, and I will try to expand a little bit more on that in the next transparency. So I hope not to confuse you with these remarks. These are on the more speculative side. So we've seen that, so this is a qualitative idea that people have mentioned from time to time, and it's an idea which is at least 20 to 30 years old. So you look at the formula for the black hole entropy, and it contains the area term and entanglement entropy, and when the bulk cutoff goes to 0, the entanglement entropy contribution becomes very large, and due to the renormalization of Newton constant, the area term is becoming smaller. And so it is tempting to speculate that perhaps in the limit that the cutoff goes to 0, so all of the entropy comes from entanglement, and the area term just disappears. Now, something like this happens in so-called induced gravity theories, which are theories where you start without the Einstein term, and then you get the Einstein term by integrating out fields. But unfortunately, those theories are not well defined, because in order to get a finite answer for the Newton constant, you need to have negative norm fields. So this is not in the context of unitary theories. And so the conservative point of view is simply to say that we should not mix the leading order answer with the subleading order answer. So it is true that the S entanglement diverges, but we should never take the cutoff so small. We should always take the distance cutoff epsilon to be much bigger than the Planck scale, and then we never run into this issue. But of course, the dreamer might say, well, perhaps there is some sense in which this is true, and maybe there is a way to define the theory so that this is true. But this equality between the relative entropies is somehow, you can view it as some evidence or some cutoff independent indication that all of the entropy or all of the distinguishability of the states. So if this is roughly saying that two states are distinguishable in the boundary only if they are distinguishable in the bulk. Of course, this was derived only for some subset of states, so it's not completely true. Okay, so that I hope I didn't confuse you with these remarks. Now we'll go continue with the review. So in order to derive the Ruta-Kanagi formula, one can start from Einstein's equations and then follow the definition of the entropy and then find the Ruta-Kanagi formula. But people have also shown how to go in the other direction of starting with the Ruta-Kanagi formula as the basic equality and then deriving Einstein's equations. Now, this has not been done with full generality. It's been really done in cases where you know the boundary modular Hamiltonian for some reason, and that can be done when you are considering states which are close to the vacuum. Okay. Now, this is sometimes said as deriving Einstein's equations from entanglement. I think that's slightly misleading. So it's really deriving Einstein's equations from the entanglement formula. You need to know that the formula is given by the area. So here the logical relationship is that from the formula, from area, we go to Einstein's equations, which, well, of course, was in terms of the curvature, right? So it's equivalent to say that we have an entanglement formula given in terms of the area, or we have a Lagrangian given in terms of the curvature. Okay, so now I'll discuss a few things about wormholes. As Daniel Harlow reviewed yesterday, we can view a wormhole as an entangled state in two separate CFTs. So these wormholes are the eternal Schwarzschild ADS geometry, or the full Schwarzschild ADS geometry, maximally extended. It has two asymptotic regions, one on one side, one on the other side. So these are two ADS boundaries joined through the interior. And this is supposed to be the same as an entangled state in this particular entangled state is called the thermophile double in the two boundary theories. Now, the integrated null energy condition along these horizons, so if you integrate T minus minus along the horizon, you find that it is positive, and the positivity of that, recall the recent entanglement-based proof, the positivity of that implies that no signal propagates through the wormhole. Now, an interesting recent observation, this is based on a paper that is to appear, so this is not in the archive yet, is that allowing interactions between the two sides, we can have actually negative energy, so we can have some energy which is negative, and then we can get signal propagation. I think this is an interesting point, and I'd like to discuss it in a little more detail. It's an interesting point because I think it will be a useful lesson for how these wormholes work. What this author said was they consider the thermofield double again, and now in the bulk they say, well, let's put some interaction between these two sides. So we put some direct interaction, some direct coupling between the operator here on the left and the operator here on the right. Okay? So we can put this interaction both in the bulk theory and in the boundary theory. Okay? Of course, in the bulk theory, it looks artificial because it's an interaction for space like. It might look at the first, at first sight artificial, but of course these two boundaries could be close to each other in the ambient space, so it's perfectly reasonable to do this and explore the consequences of this. And that's what they did. Now, when you do that, it turns out that when you evaluate the stress tensor here, there will be a diagram that has a phi field. So let's say O I should have said this is a double trace operator. So here we have an operator dual to a single bulk field, and the operator right is single bulk field here. So there is a diagram that contains a stress tensor and two phi constructions, and that's non-zero. And the answer for the energy then will be proportional to lambda, and by choosing the sign of lambda appropriately, we can make it negative. Okay, so we can always make this energy negative. And if we make this energy negative, then if we send a signal from very far here in the past, then when it crosses this negative energy region, instead of having a time delay, we have a time advance, and the particle really goes through the wormhole. Right? Now, of course, this is not in contradiction with anything. We put some interaction between the two sides, and the particle went through the wormhole. That's perfectly fine. Now, an interesting point is that one interesting point is that the particle that went through the wormhole had nothing to do with the particles that were contributing to the negative energy, or the particles whose direct interaction we were putting. So by connecting just a few of the qubits, just one field, we create the possibility of sending a signal for any other field, that you send early enough. Now, this is connected with a previous paper by Hayden and Preskill that they called black holes as mirrors. And at the time, this looked like a very weird property of black holes. And this particular configuration shows explicitly how that works. So what they said was that they consider a black hole that was maximally entangled with some quantum computer that some person had. Then someone sends some information into the black hole, a qubit into the black hole, and then this person that has the quantum computer gathers a little bit of the Hawking radiation from the black hole, just a few qubits of the Hawking radiation, and then from just those qubits and this other, let's say, entangled state of the black hole that he had, he can recover the qubit that the other person sent into the black hole. And this is exactly what is happening here. So we have the black hole in that discussion would be the black hole here on the left. The quantum computer is just the second black hole that is entangled with the first one. So here you send in some information into the first black hole. This interaction allows you to collect some Hawking radiation from this side, and then you feed it into this right side black hole, which is acting like a quantum computer. And from this, you can extract the information or the qubit that you had in the other side. Okay, so that ends the discussion of the wormholes. Now, I should emphasize that there's been a lot of discussion of entanglement entropy, but the concept in the boundary theory is not always entanglement entropy. There are other forms of entropy. And this is clear when we consider the difference or distinction between entanglement wedge and causal wedge. So let's consider a situation where we have, again, a wormhole, and we throw in some matter into the wormhole, or we consider a configuration, let's say, is time symmetric and C2 symmetric. And in those situations, the wormhole becomes a bit longer, and the two horizons become separated. And in these situations, typically one finds that the Ryuta-Kanagi surface, so the surface of minimal area, is just deep inside this wormhole, and has an area which is less than the minimal area of the horizon here. So here, this is the horizon. It has a minimal area here, and then the area increases in the future in accordance to, let's say, the classical second law. And we have some area here which classically is bigger. Now, this region, which is the region that is causally accessible from the boundary, so all points that can both receive a signal and send signals to the boundary, is called causal wedge. And this can be defined not only for these wormholes, but also for sub-regions. Here I'm just drawing this wormhole case because it's simpler to draw. And so in this case, there are these three different areas, and it's tempting to think that they should be associated to three different entropies. Or slightly more precisely, we have this, the three different entropies should be the area of this plus the entanglement entropy of this side, or the area of this plus the von Neumann entropy of the fields here, or similarly here. And recall that the object that obeys the second law is precisely this type of area, so the area of the horizon. Okay, so we expect these different notions of entropy, and the Ryuta-Kanagi formula is just giving us the fine-grained entropy from the point of view of the boundary theory. So on the boundary, we look at one side, and we have some density matrix. That's computing the entropy of that density matrix. But these other two entropies should be viewed as some kind of coarse-grained entropies. And so the idea is that we are restricting the algebra of observables to the ones that correspond to gravity fields outside the horizon, or perhaps simple operators acting within a scrambling time. And the idea is that coarse-grained entropy is the idea of considering the entropy of this is the same notion that we always use in thermodynamics, which is to say that the coarse-grained entropy is the entropy of the maximal entropy state compatible with the density matrix on the simple algebra. And there were some papers making statements in this direction. Didn't make exactly this statement, and not all properties of this have been completely clarified. So this is a problem that hasn't been completely clarified. And making a little more clear this notion of the causal wedge and exactly what is the causal wedge in the boundary theory would certainly be very useful. Okay, so now I'll have some discussion I'll go into the discussion of the tensor networks. So the tensor networks are, they originated as a method to write wave functions, as a kind of ansatz for the wave function. So the idea was to construct the wave function out of simpler objects, out of simple tensors. That's where the name tensor network comes from. And it originated as a numerical method. So people doing numerical calculations, simulations of interacting quantum systems, spin systems, and so on, they found this to be a useful method to analyze the wave functions. And they embody in a useful way the renormalization group, as we will see in a second. And there are some interesting qualitative similarities with gravity. So in the rest of the talk, I'll try to discuss this in more detail. So the simplest example is the so-called matrix product state. So we have, imagine you have a wave function of n spins. So we have n spin-and-a-half particles. And so for each spin, we have plus or minus. So we can write the wave function in the C components for the spins. So the wave function consists of 2 to the n numbers, which are this size of S1 up to Sn. So S1, each Si can be plus or minus. And then one writes those wave functions as this expression here on the right, So in terms of the trace of some matrices, so one introduces a matrix for each value of S, so S can be plus or minus. We have a D by D matrix that has D by D indices. It has D indices. And in this expression, all those indices are contracted. So the indices of his contracted here and so on. So this is sometimes represented graphically in this way. So each intersection point here is a tensor. So this matrix that has three indices. So each index is a line that comes out of the vertex. Here we have these two indices are the horizontal lines, and these SIs are the vertical line here. So a line that goes between two vertices is a contracted index. Okay, so here we have all these indices that are contracted, and so we have a line going between the two vertices and so on. So here this trace is cyclic, so we have all the indices contracted in this way. And the idea is that this is a wave function for a system of n spins on a circle, for example. Now, this type of wave functions for fixed D and very large n is describing a subspace of the full Hilbert space. So the full Hilbert space has dimension 2 to the n. And then if we only have matrices of this kind, we have 2 times d squared, so the full the dimension of the space we are spanning with these matrices is 2 to the d squared. Or even if we have them all different, we will get an additional factor of n, but this certainly will be much less than 2 to the n. So this is a subspace, but and this subspace, the things we can describe with this subspace are states that have a finite amount of long-range entanglement between different spins. And so states that if we are looking at a spin chain whose, let's say, has a Hamiltonian, and we are looking at the ground state of the Hamiltonian, and that ground state has a mass cap, then it will have a good description in terms of such a tensor network, if we take D large enough. Now you can consider networks with different structures. So here we can consider another one that is useful for describing conformal field theory, so states that do not have a mass cap, that are scale invariant in the infrared. And then such states can be described by tensor networks, which roughly look like this. So here now we have 5 index tensors, and the arguments of the wave function would be these indices here that are not contracted. And so here you should get the idea that we are really building the entanglement little by little. So we have this tensor here builds up entanglement at long distances, and here we build more entanglement at shorter distances, and as we get to shorter and shorter distances, we build up more and more entanglement. And so that's how people propose to describe wave functions in such scale invariant systems. With these wave functions, we can compute the entanglement entropy of some region. So if you have some set of spins and you want to compute the entanglement entropy, you can bound the maximal entanglement entropy you can get is given by looking at the minimal number of indices that you can cut here. So you can draw all possible surfaces here, and then you look at the one that cuts the minimal number of indices, and just summing up summing up these the dimensions of the Hilbert spaces here, we get a bound on the entropy. So this is the maximal entropy that we could define, we could get from such a wave function. And it turns out that by choosing suitable tensors, this is actually the actual entropy. And if you choose random tensors, for example, as it was done in this paper, you get indeed that the entropy is actually given by these formulas. This works a little too well because you also get brainy entropies given by the same formula. So that's a problem. Now, Swingle found that made the initial observation that these pictures of tensor networks look very similar to the geometry of hyperbolic space, and suggested that there would be a relationship, and also made this observation about the connection or similarity for calculating the entropy to the Rutiakanage formula. Now, these tensor networks are a tool that is fairly flexible and can have different physical incarnations. So we can view here, as we were discussing, as a way to write the wave function. We can also view it as a unitary transformation that takes a bunch of unentangled qubits. So let's say we have a bunch of qubits all in the, let's say, 0 state. And then by a set of unitary transformations, we create the state in the future. So here, for example, we start with 2 unentangled qubits. Here we mix them a little bit, we entangle them. Then we add here another qubit, and so on, and we start entangling them as we go to the future. Now, this looks a little bit like the Sitter evolution, and this is not a coincidence, because we can take, of course, the CFT and write it. So we're writing the wave function at some time. So we can think of the CFT as coming from time evolution up to t equal to 0, either on flat space or on the Sitter space. And so the symmetries of the problem certainly are compatible with this picture, and imply so if we think in terms of the Sitter evolution with the Sitter warp factor, we get certainly a picture like this already in the boundary theory. And then there's been some connections that's been argued that this is useful in the so-called kinematic space that I'm not going to review. But it's also interesting that we can perhaps use this picture for representing the cosmological wave function. So maybe the cosmological wave function is just a tensor network of this kind. Now, one useful property of tensor networks is that they have some properties that allow us to get some hints about the interior of the black hole. So if we can consider a thermal state, so a thermal state is again situation, the thermal field double state can have also tensor network description with again 2 boundaries, and here we have the 2 boundaries on the 2 sides, and then a tensor network that generates the state on these 2 boundaries. Here the horizontal direction is the spatial direction. And then if you evolve this state so you evolve moving both times forward, then we expect that we generate longer and longer range entanglement, and therefore we would need to make this tensor network deeper and longer. And this agrees with the idea that the spatial slices inside the horizon are getting stretched. So in the interior of the black hole, the spatial slices are getting stretched, and this stretching seems to be connected with the stretching of the tensor network. Now, one question is, which tensor network should we choose? So one idea was to choose simple elementary tensors. So we choose small tensors with small number of indices. And we can view the network as a circuit, a quantum circuit, that prepares the state out of simple operations, starting from a simple product state. And if you do this, then you can define the complexity to be the number of simple gates that you need to prepare a state. So it's reasonable to define complexity this way because so a state which is a product state is very simple, and the more gates you need to use, well, it's the harder it is to actually do it, so it's the more complex the state will be. Now, there's been an interesting conjecture saying that complexity is equal to the action. So imagine we are looking at, again, this configuration of the thermal field double, and we have 2 times, we are looking at the state at some 2 times here. Then we can consider these Wheeler-DeWitt patches, which are simply the region spanned by all spatial slices that end at these times on the boundary. And what these authors have done is they said, well, a natural thing to consider, a natural number to associate to these patches is the action. You just take the on-shell action on these patches, and then the idea is that that action is equal to the yeah, is equal to the complexity of the state. Now there is nice qualitative agreement, and in particular the time dependence that we expect here. So here we expected that the tensor network should grow linearly with time as time progresses, and indeed this action grows linearly with time in a fairly universal way. Now there are some questions. For example, evaluating this action involves getting close to a singularity here, where we cannot trust the classical gravity action anymore, or at least the two-derivative action anymore. And these formulas assume that there is no big contribution coming from here. And maybe that's a lesson, or maybe we need to understand, let's say, including the stringy corrections, understand whether indeed this is true or not. I mean, this action certainly is an interesting quantity. Maybe it has some other physical interpretation, but this is certainly an interesting interpretation for this action. Now, tensor networks can also be used to encode. Can be used not only as a way to think about the wave function, but as a way to translate between the bulk wave function and the boundary wave function. So here we are viewing the tensor network as a kind of unitary map between the interior and the boundary, or more precisely, an encoding of the bulk into the boundary. It's a kind of sometimes called isometry, or an encoding which is similar to the encoding one makes when one considers error correction, quantum error correction. So there's been several papers on this, and I think Xidong will talk about this. And so here the idea is that so we put in the bulk states here in these indices, and then we have some tensors that transfer this sort of quantum information into the boundary indices. So in summary, I would say these tensor networks capture many qualitative features, and people are exploring them more and more and finding more qualitative features that match and look very interesting, and are giving some light to how holography works. Now, a main drawback that they have is, or a main defect that they have so far, is that we cannot see local Lorentz invariance in the bulk. So, I mean, this is only a very coarse picture. We don't get a picture, we don't get the local Lorentz invariance we get in the bulk gravity description, which is so fundamental to the gravity description. So in conclusion, we've seen that quantum entropy is a useful tool to prove general results in quantum field theory, and here these non-trivial results come from an interplay between Lorentz invariance and the positivity of the density matrix, which is related to the unitarity of the theory. So unitarity and Lorentz invariance give these results, and one can not only prove these results, but also understand better how the degrees of freedom of quantum field theory are entangled. If you consider gravity plus quantum field theory, and using some of the results of the previous bullet point, we find interesting entropy statements and statements about what the proper definition of the entropy is, and one can prove properties of these entropies, such as the second law, the Busso bound, and various properties of holographic entropy formulas. The study of these wormholes, I think, will help us constrain how space-time emerges, and that is probably another tool that we have for understanding how all of this works. And finally, I would say tensor networks capture very interesting properties of black hole geometries, but not back Lorentz invariant so far. Thank you very much.
Questions? Can you explain why the in the wormhole situation, the space on different boundaries can have interaction.
Well, the different boundaries are far away from each other in the bulk, right? But in the ambient space, they could be close to each other. So in that way, for that reason, they could have some interaction. So this configuration could be, let's say, this wormhole could be dual to some, let's say, field theory that some system of spins that an experimentalist has in the lab, right? So has one side of the wormhole corresponds to a bunch of spins, let's say, in one duer. The other corresponds to some other spins in the other duer. And he can just put some interactions between those spins. So, and then that in the bulk would be dual to that interaction we saw at the boundary.
There's a question here.
There are two opinions about the Maldacena network. It can be viewed as the time slice of the AS, or it can be viewed as the kinematic space. If we view the Maldacena network as the time slice, it can match to the subsequent proposal. The complexity equals to the maximum volume of the in the AS.
Yes.
But if we view the neural network as the kinematic space, can match to the proposal that complexity equals to the action. Can these two things have a relationship?
Well, as I was trying to say, these tensor networks are a very flexible tool. They can arise in different situations, and maybe they are not all equal. You can view them as a spatial slice. I also mentioned when I was talking about the zeta revolution, that was more like a time slice, a slice that goes along time. Yeah, different applications might see different tensor networks, and there might not be one that is good for everything. So in the discussion of the action, the philosophy was that you look at the simplest network built out of simple pieces that can describe your state, and then you count the number of gates of that network. So that's one definition of some construction of the network. For some other application, like the one in kinematic space, we might construct it in a different way. And yeah.
There's a question from Andy.
In de Sitter space, there's this puzzle that if you think there's 1 degree of freedom per Planck volume, and then de Sitter space is expanding, or any expanding universe, you seem to be getting more and more degrees of freedom, which is hard to reconcile with unitarity. Does the tensor network picture give us any more satisfying way of thinking about that? Or?
No, not as far as I know. So in this picture, you just simply you have those same degrees of freedom you were mentioning. So each zero here is one additional degree of freedom you're bringing in. It's just you're bringing it in the vacuum, but yeah, it doesn't offer any further enlightenment.
There's a question there.
So, the tensor network has similarities to Reggie calculus, even though for it's very somewhat different in the sense that you have a rigid framework, rigid network, and you're doing some degrees of freedom. But one could imagine that this is a particular background and you're fluctuating, you have that piece mixing. Do you have any thoughts about that?
No, I don't have anything useful to say. Yeah, it would be nice to go more directly between the bulk picture and the tensor network picture. I think what you're hinting to is to the idea that you start from the bulk description and then you build some objects which look like the tensors that appear in this description. And yeah, it would be nice to do that. I don't know how to do that.
Yeah, that's the question from Juan. So you described the relationship between containment and the area, and indeed potentially this speculation that the black hole would be containment. But at the same time, there's an important match that we have in string theory where we call the microscopic entropy of the black hole matches the effect on the area as well. Would we say that we have a self-consistent picture where both these ideas are
Well, I would in this context, I think, so the matches we have in string theory consist of replacing the black hole and the geometry and so on by some system of branes, and depending on the original calculation of Strominger and Buffer, they just simply continue the coupling to a region where you can calculate it, and then you argue, well, for BPS states you can do this without changing the number of states, and then you can calculate it explicitly. So it's a more indirect way to calculate the entropy. So this whole discussion was in trying to understand where the qubits actually are. So where should we think of quantum information residing in the bulk theory? And even though we have this wonderful agreement between gravity and this D-brane picture, we would like to have better understanding from the bulk point of view.
Last question.
Sometimes one hears that proofs based on the entanglement entropy are not fully satisfactory because it's hard to regulate preserving Lorentz invariance and other properties that they use to the proof. Is this a serious concern, and can we get wrong results if one is not careful?
So these results that are based on relative entropies are finite. These relative entropies are UV finite, and if you use relative entropies, then you would get correct answers. Now, it could be that there are, as in any proof, there could be subtleties. The proof of the C theorem, for example, uses some strong pseudo-additivity, so it's a slightly different character. But all the consequences all these results, all these theorems have not been contradicted yet, let's say. All the proofs that have been found through entanglement entropy didn't lead to any contradiction. So let's say that's a sociological explanation for why we should trust them. Yeah, maybe there are better methods to prove some of these things, but these methods look pretty strong. There are many consistency checks of the method, and you argue these very general answers, very general results.
Okay, there are two more questions.
Do you expect any important difference in all this discussion if the quantum theory is non-relativistic?
Yeah, there are important differences. So let's say if you have a lattice model, for example, and you divide the lattice into two parts, you will not get a modular Hamiltonian that is local, for example, or even thermal, like we had in for relativistic field theory. So there are such differences. Of course, general properties of entropy are the same, but you will not be able to prove the same results, like positivity of null energy, where we couldn't even talk about null energy.
Yes. It seems there's a natural geometry in this network. There's a shortest distance between two points that seems equivalent to this hyperbolic geometry. That's one. Another thing is for this network, the short range entanglement things can be worked out by local transformation, and only the long range entanglement remains. Can you comment on how to characterize this long range entanglement?
Well, certainly the tensor network characterizes it. This is a very good characterization. I'm not sure what we can calculate entropies. We can calculate various other notions of entanglement, mutual information, and so on. Those are the techniques that people have used to characterize entanglement. Regarding your point about notion of distance, yeah, you could define those notions of distance you mentioned, but the target we want here is to define the notion of distance that we have in general relativity. So ideally, in this string theory conference that we want to talk about quantum gravity and so on, so a very basic property of classical gravity is Lorentz symmetry. And this is only a property that is missing in this discussion. And it's missing in the statement that you made about the geometry. So we really need something better for us. So So these are all hints that are interesting, but here there is an opportunity for you to find, let's say, some tensor network which also is relativistic, or maybe it's not a tensor network, maybe it's something else, but certainly an opportunity for you to find it.